Welcome to today's session. We will go through OCaml Modules, which is part of the language section in OCaml.org. So we have gone through under Learn Language. We've gone through all of these sections. We start off with the options, arrays. We did sequences. So I want to finish modules, functors and libraries, and then we can finish up with the data structures. And then the idea is to go to the other sections here, like platform and so on. Okay. So let's get started with the module section here. Let me share the link in the chat so you can follow along. Feel free to ask any questions in the chat. Okay. So in this tutorial we are going to look at how to use and define modules. What are modules? Modules are collections of definitions. They're grouped together, and that's how most of the OCaml software is organized. So we already covered the prerequisite sections, values and functions, and basic data types and pattern matching. So let's look at some practical examples here. The first one is file-based modules. So in OCaml, every piece of code is wrapped into a module, and you can have a module within a module or a submodule, just as how we can have different directories in a file system. So to demonstrate this, let's create a new demo directory here, and the tutorial asks us to use two files. So let's create athens.ml and berlin.ml. Each correspond to the module Athens and Berlin respectively, right? So I'm just going to use nano here to demonstrate the purpose here. So we're going to say let hello print n line hello from Athens. Okay. Let's create berlin.ml. And Berlin, I'm just going to call the Athens module and the hello function. Okay. Now, in order to compile this project, we have to define two configuration files. One is called the Dune project, which has project-wide configuration. So, if I check OPAM switch, I'm currently on 5.1.1, and if I do OPAM list, I have all these packages installed, and I specifically have Dune 3.14.2, right, as of this installation, but we can use 3.7 as the base. So I'm going to create Dune project file, specify Dune is 3.7, save, and then we create the actual Dune file, which is used to build directives. So a project can have multiple Dune files, one per folder. So it specifies how to build the respective folders. So here in this case I'm going to just build the executable, and the executable is called Berlin. Okay, so we have created athens.ml, berlin.ml, Dune file and Dune project. So now to build these modules, we have to run OPAM exec -dune build. It compiles it. Now we can run it using opam exec dune exec /berlin.exe, and we have the output from berlin.exe, which actually calls the Athens module hello function. Right? It's a very simple example. So the parameter .berlin.exe is not a file path. Okay, it just means that you want to execute the content file berlin.ml. The executable file is stored and named differently. Right. So if you look at, there is a build folder, then inside that there is a default folder, then there you have the berlin.exe, but when you are trying to run it, you basically specify it as /berlin.exe. Okay. Now if you are starting a new project, generally you can use dune init project as the command name, but we can do a session on dune also in future. But let's continue with our modules example here. Now in berlin.ml we used athens.hello to refer to the hello function in athens.ml file. Okay. So generally to access something from a module, we just use the module's name, which starts with a capital letter, and then whatever method you want to call, you specify it, prefix it by dot, and then whatever you want to call it. Now this can be a value, a type constructor, or anything that the module provides. Of course, we are using modules a lot. You can actually call open, which basically brings the modules definitions into scope. So in berlin.ml we could have written it as open Athens and call the hello method directly. So using open is actually optional, especially when we use like common modules like list, arrays and options and so on. Now modules like printf, they provide names that aren't necessarily subject to conflicts such as printf. So using something like open printf and then calling printf.printf, okay, can be avoided. So in this example here we see that they call open printf, we're having a let data list, then we're calling iter on the elements of the list. Okay, so the standard library is stdlib, and it contains a lot of submodules like list, option, either and so on, which you've already seen. So by default the OCaml compiler will open the standard library, so it is as equivalent to specifying open stdlib at the top of the file. Now you can open a module inside a definition using the let open in construct. So let's try that. So I'm just going to run utop here. Okay, so I'm going to say let list sum square m is equal to let open list in init m fund id mapped to map I is I times I, pipe it to fold left plus 0. Welcome Promethean Sacrifice. How is your stream today? Right. So in this example, Promethean is still streaming. It's good. So Promethean sacrifice streams on OCaml and SE packager. So I would encourage you to follow him on Twitch. So in this example, we have seen opening a module inside a definition, right? We can also access a notation to an entire expression, right? So let's try this here. Let array sum square m array dot init m fund id map and I into I, and then we're calling fold left plus function and initial value 0. Okay, right. So anything defined in a module is accessible from other modules. So as we saw, this can be values, it can be functions, it could be types or even submodules, anything that is public. Now we can of course restrict what we want to expose in the definition to the outside, right? So we must distinguish between the definitions inside a module and the public declarations of the module. So in OCaml, the ML file contains the implementation or the source, and the .mli file contains the model interface. So let's look at an example here. Now when there is no MLI file provided, an implementation that has a default interface is taken into account and everything there is public, right? So let's go back to our example. Exiting UTOP. So we have Athens and Berlin. So we want to copy Athens to Cairo.ml, and we want to update Cairo.ml to say let message is equal to hello from Cairo, and then we say let hello as print inline and message. Okay, so Cairo has two interfaces. One is a value which is a message of type string, then we have a hello which is a function. It takes a unit and returns a unit, right? Now we can define an interface for the Cairo module. Okay, now just to demonstrate public and private interfaces, let's make just the hello as public. So we'll say Cairo.mli. I'm specifying only the hello function. It takes a unit and returns a unit. And in OCaml we can use comments within open parenthesis and asterisk, right? So I'm just going to say hello displays a greeting message. Now I'm not exposing the message, so message now becomes a private definition. So this kind of double asterisk documentation is useful for the OCaml documentation tool called ODoc, right? So it's a good habit to document your MLI files. Now let's use this Cairo module. So we'll create a new ML file called Delhi. So here we're just calling Cairo.hello. So we have all of these files. Now we also need to update our build to reflect these new files, right? So nothing changes in Dune project, but in our Dune file we have to build Delhi. So we make this executable as plural executables, and then we add Delhi right? So let's build this opaml exec dune exec dot slash berlin dot exe. It builds either the names or the public names field must be present. Did I make a typo somewhere? Let's check. Delhi.ml Cairo.hello, that looks fine. Oh, we have to make this plural also. It should be names. Right. Now it compiles and it runs berlin.exe, it prints the output. Right. Similarly, we can run opaml exec dune exec dot slash delhi.exe. So it'll again compile this file and it sends hello from Cairo, which is from the Cairo module. Right. Now we can verify that the Cairo.message is actually private. It is not public. So suppose if I change in delhi.ml to say print inline Cairo.message. Let me just move this to a comment, right? So if I try to compile this, it should throw an error saying unbound value Cairo.message, because this is actually not exposed in the MLA file. Good. So let's move on to the next one. So function and value definitions are either public or private. This also applies to type definitions. So this is an example of two new files. Let's create those files. We have exeter.mli, which is an interface file. We have type lf is Ada or Alan or Alonso. Type is GML, val GML of bool, bool to GML, then val GML flip is GML to GML, val GML to string is GML to string. We have another type, Dalet is private, Dennis of int or Donald of string, or just Dorothy. Then we have val Dalet of int string, which is either option, and returns a Dalet. Hopefully I have not made any typos there, but we can check this once we try to run this. Let's create exeter.ml file. So type alf is Ada, Alan, Alonso, type bit is bool, type GML is Christos or Christine. Let GML of bool takes a B. If B bet, then Christos, else Christine goes. Those are the two constructors we have. So let GML flip is a function, Christos, Christine, we're just flipping the values there, Christos, okay. Then we have let GML to string x is Christ and match x with Christos OS, or matches anything else, you just return INE. Okay. The type dalet is Dennis of int or Donald of string or Dorothy. Right. And then we have let dalet of function none Dorothy sum either dot left x Dennis of x sum either right of x Donald x. Hopefully I have not made any mistakes there. Let's update the Dune file here. So already we have executable names. We have adding the modules as well, Berlin, Delhi, right, and then creating the library name exeter. So the modules exeter and mode is using byte mode. Right. Now I want to load all of these interfaces and implementation code in UTOP so I can directly start testing them. So for example, I can do opam exec -dune UTOP. So it compiles everything and loads the environment into UTOP. So now I can actually open the module, open exeter. I can say what is show aleph. Is of type which has constructors Ada, Alan and Alonso. Type aleph is public, right? So values can be created or accessed. If I ask for show bet, it says unknown element because bet is private. It is not accessible outside the implementation. Let's try out more examples here. So we have show gimel, which is a type, Christos, which is unbound constructor. Can do show val gimel of bool, it's a function we wrote. Pass true to gimel of bool, gimel to string. So we return Christos. You can ask for true gimel of bool, gimel flip, gimel to string, and it returns Christine, right? So type gimel is abstract. Values can be created or manipulated, but only as function results or arguments. So we have used the given functions to receive and return values. So some more examples here. Let's do show dalet. Okay, I say Donald 42. Donald is of string, right? So it says expression has type int, but an expression was expected of type string, right? So we wanted string here. Dalet of sum either dot left 10. This Dennis of 10. Dennis is of type int, and I can define functions here. Dorothy as Dorothy, Dennis as Dennis, and doesn't take any argument there. We ignore the argument, say Donald. So we can define these functions. So when you are writing code in a project or module, you can start with something basic, load in UTOP, and then you can start to build and test on top of that. So it's very nice to use this REPL environment when, and that's the whole idea of functional programming, right? It's very easy to get started and work with. Right, so in our case, the type dalet is read only. Pattern matching is possible. but values can be constructed by the provided functions. Good. So abstract and read-only types can be either variants or it can be records or aliases. So we can access a read-only fields value, but creating such a record requires a helper function. So now let's look at example of submodule. So module can be defined inside another module. So here they are giving two files to be created. Let's create exit from utop. Let's create florence.ml. So I say module hello struct let message is hello from Florence. I say let print inline message and let print goodbye print inline goodbye. Right, this is Florence, and then we create Glasgow. So say let Florence.hello.print, then we call Florence.print goodbye. So in the case of submodule, to access it, you change the module name. So in this case, we are calling Florence module. In that submodule hello, and then we call in the print function. This one, right? That's how you access submodules. Now you can define a submodules interface also. You can provide a module signature. So how do we do that? So in florence.ml, we can say module hello. We say this is a signature. Val print takes a unit, returns a unit, and then end structure, then the actual value and function here. Okay. Now you can also write it differently. So this is a third way of writing florence.ml. So what they say here is define it as module type hello type equal to signature val print, you end this, then you say module hello and hello type is struct message print in. Okay. So first we define a module type called hello type, which defines the same module interface. Now instead of providing the signature when defining the hello module, we just use the hello type module. Right. So hello is hello type module. So this will allow us to write interfaces that can be shared by several modules. So it sort of separates that concern there. Of course, the implementation satisfies any module listing with the contents. Of course, a module can have several types, and there is subtyping relationship between these module types. Good. So let's look at displaying a module's interface. So again, if we go back to utop, I can ask for unit. So that's a module unit signature type T is got equal, compare, and toString defined in the interface. Now you can also create the MLI file from the implementation file. How can we do that? So if we go back to our sources, right? So I can say OCaml C -c -i compile, generate the interface for say .ml. It tells me that this should be the type signatures required in the MLI file. Now we can also include a module if it's missing. So let's create this extlib.ml file, and using the include directive. So module list include stdlib.list, let unconst is a function, for empty list return none, there is a head and a tail, return sum of head and tail, end. Right, so you can use the include directive. So this creates a module called extlib.list. Okay, that has everything from the standard list. In addition, we have defined a new unconst function. Let's say you want to import a module and then add some functions that you want to use only in this code, you can do that. So if you want to override the default list module from another ML file, we just have to open extlib at the beginning. We actually start using this particular module and its functions. Modules can have state. So an example given here is the random module from the standard library. So it's got two functions, get state and set state, to read and write access to the internal state, right? So let's try this in utop. So let s is random dot get state. Okay, so I'm calling random dot bits. So it returns me one random number here. I'm calling it again, gives me a different result. But now I want to set the state to the initial state that I set s with, right? Now if I again call random dot bits, is the same initial sequence number that I got here, right? So there is some state that is being stored here. So to conclude, modules are the basic means of organizing OCaml software. It has a collection of definitions under a name. There can be submodules which allow you to create a hierarchy of modules. The top level modules must be files, the basic units of compilation. Every module has an interface and it lists the definitions that the module exposes it, which is public. By default, all the modules interfaces are exposed unless you restrict them in the interface syntax, the MLI file. So next we will, the next session we'll go and learn about functors. We'll look at libraries which are compiled modules together, and we look at high level packages, right? So with that, let me stop the recording. Let me see if somebody whom thanks for joining, Matami. I will make the recording available on YouTube. So I have uploaded the previous session, which was the sequence module here, the last one, and this one will be modules. Next one we'll do functors in the next session. And I've also pushed the notes to my GitHub repo. Let me share this links as well. So I will probably just simplify the notes so that it's good for a quick reference. Let me share the GitHub repo as well. In the chat. Let's let me stop the recording and then let's raid somebody else who is streaming now.